Our next set of functions, we want to learn how to differentiate, and so we're going to look at the trig functions. In order to do that, I just want to point out some limits. I won't end up using all of them, but if we think about our trig functions as x approaches 0, what's the curve doing? And the sine curve is approaching 0, because we know it goes through the origin. The cosine curve is approaching 1, and our tan curve is also approaching 0. Okay. Now I'm going to use this circle here, and what I know is how to find the area of a sector. Let's say the angle at the centre is x, the radius is 1. But what I do know is if I draw that chord in, the area of that smaller triangle that I've just drawn in must be smaller than the area of the sector. If I was to draw in a tangent and then join it up with OC, I can create a right angled triangle there too. And what I know is the area of this right angled triangle must be bigger than the area of the sector. I can work out the length of AB using trig. It would work out to be whatever the tan of x is. Okay, well let's find some values for those areas. The smaller triangle, I'll use our half AB sine theta in the middle. And for the sector, we know it's a half times the radius squared times the angle itself. And for the right angled triangle, half base times height. Well, there's some common factors there that cancel out, and I end up with x is in between sine x and tan x. I'm going to divide all of that by sine x, and I get this interesting result that 1 is less than x on sine x is less than 1 on cos x. But if I just consider when x is approaching 0, the right hand side becomes 1 as well, because we said cos x is going to approach 1. So we're saying x on sine x is in between 1 and 1. Therefore, that limit must be 1. It's what's known as the small angle theorem. If you're working with very small angles, the sine of the angle is approximately the same as the angle itself. This is going to be useful for what we want to do, this particular limit. Okay, well before I go into the calculus, let's look at how we can play with that limit. You see something like this. The key is to make the numerator, in this case, the same as the angle itself. The angle will be the same as the sine of that value. It already is in that, so I know that limit will also approach 1, because if x approaches 1, if the angle approaches 0, then 5x will approach 0 as well. But if I get one like this, hang on, I want that numerator to be the same as the angle, so I can change it. I'll make it 3x on sine 3x, but to balance it out it'll be times a third. I know the fraction will approach 1, and so we'll get 1/3 as that one. That's going to become useful, that idea. So let's have a look at the sine function. How do we differentiate it? Well, I'll go back to first principles. Function x plus h minus function x all over h. Now the sine of x plus h we know goes sine cos cos sine. If it's the sine, it's the sine. We have this problem. I can't substitute 0 in for h here because I've got the 0 on the bottom of the fraction. If I now split this up into two things. The first one, I've made it cos x times sine h on h. There's that limit, I know. That's going to be nice. The second one, sine x, if I group the sine x's together, I got cos h minus 1 on h. Need to do a little bit of playing around with that. I can use my double angle results to change that cos h. Remember, cos 2 theta is 2 cos squared theta minus 1. So cos h, double angle, so it's double a half h, must be 2 cos squared h on 2 minus 1, but then minus the other one we got here, makes it minus 2. Okay. We know cos squared minus 1 is sine squared, so I can tidy that up a bit more. We're getting closer to being able to find a value. Problem is, our limit wasn't sine squared on h, it was sine. So what I'll do is, I'll rewrite it as sine h on 2 times sine h on 2. I can now do it because the sine h on h will approach 1. Now in the second one, the angle is the same as the other side. So I know that goes to 1. And then sine h on 2, well that's just sine of 0, that goes to 0. I end up with cos x times 1 plus sine x cos x. So simply differentiating sine x, I get cos x. To generalise that, the function will now be the angle. The sine of function x, we differentiate the function, the angle. That goes out the front. The sine goes to cosine. The angle does not change. So it's cos function x. Now let's attempt to find the derivative for cosine x. I now know how to differentiate sine x. I can rewrite cos x. Remember, they're complementary ratios. So that'll be the sine of pi on 2 minus x. And I can now differentiate that using the rule that we just worked out. Differentiate pi on 2 minus x, I'm just going to get -1. Sine goes to cos. The angle stays the same. Hang on. The cos of pi on 2 minus x, complementary ratios, that's sine x. So differentiate cos, it goes to minus sine. So generalizing that one, cosine of a particular function, differentiate the function, but it'll be minus that derivative and then the sine of that function. Let's do tan. I now know how to differentiate sine, I know how to differentiate cosine, but I can rewrite tan as sine on cos. We'll use a quotient rule. Square the bottom, cos squared. Right down the bottom, diff the top, cos times cos, cos squared. Minus, right down the top, sine x, diff the bottom, differentiate cos, I get minus sine. It becomes cos squared plus sine squared on top, which of course we know is 1. So it's 1 on cos squared, which is sec squared. So differentiate tan, we go to sec squared. Generalise that one, same deal. Differentiate the angle times sec squared, the function x, which was the angle. Okay. So differentiate sine x cubed. X cube's the angle, 3x squared cos x cubed. Okay, sine goes to cos, the angle doesn't change. Tan of 1 over x. Differentiate the angle. Differentiate 1 on x, I'll get -1 on x squared. Tan goes to sec squared, the angle doesn't change. The log of cos x. So actually it's a log function that we're differentiating. To differentiate a log function, we now know it's derivative on function. What's the function? The function is cos x. Okay. So derivative of cos x is minus sine x over that function is cos x. Well, that's an answer, but we've got a better answer because we know sine on cos is tan. So I get minus the tan of x. Tan to the power of 5x. Remember in trig we put the power next to the ratio itself. So that's really saying tan x all to the power of 5. So it's a chain rule. Bring down the power, 5. Lower the power, 4. Diff the inside, well the inside's tan x. Differentiate that, sec squared. So 5, 10 to the power of 4x, sec squared x. Cos e to the power of x. So it's a cosine function. The function is the angle, so e to the power of x. Differentiate e to the power of x, world's easiest derivative, is e to the x. So we get e to the x, but cos goes to minus sine, minus e to the x, sine e to the x.